Hello, my dear students, and welcome back. I know exams are right around the corner, and there's one chapter that always seems to cause a little bit of stress, and that's organic chemistry. But don't you worry. Today, we're going to do a super fast, super easy revision to make you feel completely confident. You know, so many students tell me, "Sir, organic chemistry feels like my biggest enemy." All those new names, the weird-looking structures, the rules, it can feel like a lot. And hey, it's totally okay to feel that way. But I promise you, it's not as scary as it looks. So, cello, let's turn this enemy into your best friend. In just the next few minutes, we're going to break down the most important ideas you absolutely need for your exam. We'll look at why carbon is so special, how to draw molecules, the secret to naming them, and what isomers are. Ready? Let's begin. Okay, first things first. The whole entire world of organic chemistry, it's all about one element. Just one, and that's carbon. You can think of it as the superstar, the hero of the story. Its special powers are the reason we have millions and millions of different organic compounds all around us. So what are these superpowers? Well, carbon has two main ones. First is something called tetravalency. Now, tetra just means four, so this means carbon can form four strong bonds. It's like it has four hands to connect with other atoms. And its second, amazing superpower, is catenation. It's a fancy word, but it just means carbon atoms love to link up with other carbon atoms, forming long chains and even rings. This is the real secret behind the huge variety of molecules we see. Now, depending on how carbon uses its four hands to bond, the molecule gets a specific 3D shape. And this is all because of something called hybridization. It's really simple. Just remember this. If carbon forms all single bonds, it's sp3 hybridized, and you get a tetrahedral shape. If it has one double bond, it's sp2, and the shape is flat, or trigonal planar. And if it forms a triple bond, it's S, and the molecule is a straight line, completely linear. Okay, let's put that knowledge to a quick test. This is a classic exam question beta. Look at the ethene molecule right here. Can you count how many sigma bonds and how many pi bonds there are? I'll give you a hint. Every single bond is one sigma bond, and a double bond is always one sigma and one pi bond. Go on, give it a try. So did you get it? The answer is 5 sigma bonds and 1 pi bond. Let's see how. There's 1 sigma bond between the two carbons, then 4 more sigma bonds for each of the hydrogens. That's 5. And the second bond in the double bond, that's our 1 pi bond. See? You got this. Well done. All right, fantastic. Now that we know a bit about the molecules, let's see how we draw them. You know, just like an architect needs blueprints to build a house, a chemist needs different ways to draw a molecule to understand it. Let's look at the 3 main blueprints you need to know. So, the 3 ways are, first, the complete formula, which is, well, complete. It shows everything. Second is the condensed formula, which is a neat way to write it without drawing all the lines. And third, my favorite, the bond line formula. This is like the chemist's secret code. It's super fast and easy once you know the trick. To make this super clear, let's just take one simple molecule, butane. Its formula is C4H10, and we'll see how to draw it in all 3 different styles. Here's the first one, the complete formula. You see? Every single C and H atom is written out, and every single bond is drawn as a line. It gives you all the information, no confusion. But you can imagine, for a very big molecule, this would take a lot of time to draw. Now to make life easier, we have the condensed formula. Look how we just group the hydrogens with the carbon they're attached to. So butane becomes CH3, CH2, CH2, CH3. It shows exactly the same connections, but it's much tidier and faster to write. And finally, the coolest one, the bond line formula. This simple zigzag line, believe it or not, this is butane. How? Well, here's the secret code. Every endpoint and every corner of the line is a carbon atom, and we just assume that each carbon has enough invisible hydrogens to make 4 bonds. It is the fastest, cleanest way to draw organic molecules. Okay, we know how to draw them, now let's learn how to name them. To avoid confusion, chemists all over the world agreed on one system for naming compounds. It's called the IUPAC system. Think of it like a game with a few simple rules, not some big, scary textbook chapter. And the magic formula for winning this naming game is right here. Almost every name has 3 parts. A prefix, which tells us about any side branches, a word root, which tells us how many carbons are in the main chain, and a suffix, which tells us what family the molecule belongs to. That's it. Now that middle part, the word root, is the most important starting point. It's based on the number of carbons in the longest chain. 1 carbon is meth, 2 is eth, 3 is prop, and so on. You have to memorize this little table. Okay, beta, it's your cheat sheet for naming everything. And here are the 3 golden rules. Rule 1, first always find the longest possible chain of carbons. That's your parent. Rule 2, number the carbons in that chain, but start from the side that gives any branches the smallest possible number. And rule 3, name the branches and just list them at the beginning of the name alphabetically. Simple.
All right, let's move on to a really interesting idea. You know, sometimes in chemistry you can have molecules that are like non-identical twins. They have the exact same molecular formula, so the same number of carbons, hydrogens, everything, but they are actually different molecules because the atoms are connected in a different order. These are called isomers.
For your exam, you mainly need to know 2 types. First is chain isomerism. This is when the main carbon skeleton itself is different. For example, one is a straight chain and the other is a branched chain. The second is position isomerism. Here, the skeleton is the same, but the position of something attached to it, like a functional group, is different. Let's look at an example to make it clear. Take the formula C5H12. This could be pentane, which is just a straight chain of 5 carbons. Or it could be 2-methylbutane, which has a chain of 4 carbons with a 1-carbon branch. See? Same formula, C5H12, but a different carbon skeleton. These 2 are chain isomers.
And what about position isomers?
Well, look at C3H8O. We could have the OH group on the first carbon, that's propan-1-ol, or we could just move that same OH group to the second carbon, and now we have a totally different molecule called propan-2-ol. The main chain is the same, but the position of the OH group has changed. They are position isomers. And just like that, we've done it. We've covered the most essential, the most basic principles of organic chemistry. See? When you break it down into small, simple ideas, it's not that difficult at all. You have truly mastered the basics. So for your exam, just remember these key points. 1, carbon is special because of tetravalency and catenation. 2, we can draw molecules in 3 ways: complete, condensed, and bond line. 3, naming is as easy as prefix plus word root plus suffix. And 4, isomers are twins with the same formula but a different structure. Got it? You are brilliant, and you have worked so hard. Don't you worry about a thing. Beta, just go into that exam hall, be calm, and remember everything we talked about. Go ace your exam. All the very best from my side.